Good morning. Ready?
Yes.
We are here this morning. Topic 3, fundamental principles. Today, class, we will be learning the advanced mathematics associated with design. You will have a lot of fun doing this topic. It is fundamental to your learning knowledge. Boring. Fundamental. See, now, this again, remember. Wow, did you see that? How did that happen? That's what we're going to learn about. Sudden things can happen that can trigger other things that you may not expect. This is the goal behind understanding, the philosophy of why and how things work. And then you can dig into the physics and the math. If you understand the physics and the math, you can do amazing things with optimizing things and discovering geometries that other people will never find. But in order to even start applying the physics and the math, you have to understand the philosophy, the principles behind how things work. And they are both fun, yes, and you got to be a little crazy sometimes to actually really understand what the philosophies are doing. So let's dive right in. You can see this range of topics. Now these apply primarily to the mechanical arts and the different types of engineering, whether it be chemical, electrical, aerospace. You'll find similar types of fundamental principles, often analogs of these. We're going to be focusing on these in the mechanical domain now. And as you look across the different images here, you'll see different things that will come about in the following discussion of the topics. And remember, I want you guys, as you're looking at stuff, to take it all in, and your eyes should scan everywhere at once while you focus on what you need to, and for your peripheral vision and peripheral mind thinking, always be aware of things on the side. So as you're thinking about Occam's razor, which you'll learn about in a minute, you should also be keeping in mind structural loops. And as you're looking at a design or thinking of a design, if you too want to be the master designer that you want to be, all of these things at once. Okay? Let's dive right into Occam's razor. Occam was this really cool dude. He lived 900 years-ish ago, 800 years, depending on what your time warp is. And Occam said, hey, keep things simple. And in actual, the reality is a problem should be stated in its most basic and simplest terms. Don't start complicated. The simplest theory that fits the facts of a problem is the one that should be selected, we should say parentheses first. Start simple. Remember, the universe loves you. You'll have plenty of time for complexity. You would no danger of being bored. And then we use what's called limit analysis to check our ideas. Limit analysis is, hey, if it was all the way over here, what would it be behaving like? If it was all the way in the other direction, what would it be behaving like? And then often, what's in the middle? Let's do an exercise to help you learn about how to actually apply the principle of Occam's razor. Occam's razor means you want to cut through all the chaff and see what's there. How do you use this in design? Everything in design has a cost. Everything in design has some level of performance. Generally, as you get higher performance, the cost goes up. Occam's razor as a design principle allows you to say, let's go as far as we can for as little increase in cost as possible before we have to start paying a lot of money to get increase in cost. And this is where you want to put yourself, right at the root of this curve jumping up. Then what do? Then it's time to jump to another technology that may initially have been more expensive, but it'll take you further along before the cost starts to go up. Okay, so I want everybody to get out your notebooks, which you obviously have open and are taking notes on a lot. Draw a square. See, I just drew a square and it took 1/10 of a second. How many people went out and opened up their laptops and started firing them up and getting their computer design programs ready? Not a whole lot. Because you see, to draw a square fast doesn't cost much. And I could draw all kinds of squares. And I could even draw a pretty accurate square compared to the first one. And I'm just slowly moving along here. Draw a square that is 10 centimeters by 10 centimeters plus or minus a half a centimeter. Uh-oh. Now I've got to be a lot more careful in drawing it. And now draw that same square, and you see now I'm moving out along here. Draw that same square that's 10 centimeters by 10 centimeters plus or minus 1 millimeter, and it's square to within 1 degree. Oof. I got to get my ruler out, and I got to start doing this a little more carefully. We'll use a more vibrant color, and let's see, I go from here to here. And you see what it's doing? It's starting to take a lot more time. And you're now starting to go up here. That's a pain. So what I should be doing is jumping to my computer and turning on my computer with a basic drawing program. And that'll take me out. And I said, well, I want you to draw me a square where the length of the side is equal to the height of your Cocker Spaniel times the mass in kilograms of the spaghetti you ate last night. Huh? Oh man, now I got to calculate. Well, now you're going to go and you're going to fire up a parametric solid modeler where I can enter in equations that drive the dimension of the side, and I'm going to write the equation into it. So you see, to just draw a square, it's foolish to go and take the time to do that. All right? So this is like appropriate analysis, which we talked about in one of our earlier topics. And what Occam's razor is used for in design is put the appropriate amount of effort into it. In other words, the cost, because time is money, for the performance level you desire. When you start finding yourself running in place, stop, say, okay, do I want to keep on this technology curve, or is it time to look around for new technologies, new approaches to the problem, new strategies, because you don't want to get stuck in a rut where you just pay a lot, okay? In addition to the normal term Occam's razor, it's often called KISS. Keep it super simple. But don't forget the MISS principle. Make it super simple. You've got to be able to design things to be made simply. Hand in hand with Occam's razor goes Newton's laws. So our friend Mr. Newton here, and there's all the wonderful stories about him and the apple tree, blah, blah, blah. The moral of the story is, ran a whole bunch of simple experiments, and from those simple experiments deduced Newton's laws. The first, second, and third laws are invaluable in design. They're catalysts which help launch many an idea. Simple things like conservation of linear momentum, conservation of angular momentum, conservation of energy. If you haven't had a basic physics class, there's plenty of online material to go and take those basics physics classes and learn this stuff. And how is it used in design? For example, you want to make a launcher for, maybe you're entering the pumpkin chunker contest. How do you know how to launch your pumpkin to get on the trajectory to make it go where you want? Okay, and then how much energy do you need to have in your spring system to make your pumpkin go from this point to this point? Conservation of energy. So these laws are absolutely critical for particular in machine design, moving from one point to another. Remember last time we showed how if I want to take a mass m and move some distance d in some time t, the power required to do so goes like the distance squared over the time cubed times the mass. Okay? So think about that. Where did this come from? Newton's laws. Now, let's move on to the next very important part of that, and that is what are called free body diagrams. In a free body diagram, what we're doing is we're looking at the system, and if you've done your reading, which you probably have, you're thinking ahead, Oh, he just told us in this long list of fundamental principles, always be thinking at everything at a time, right? Okay, good. Free body diagrams. I'm thinking ahead to structural loops. Okay, good. I got it. So when you're looking at a machine, and what's the purpose of a free body diagram in Newton? Newton, action and reaction. You push on something, it pushes back with equal amount of force. So when I'm looking at this gear train here, for example, this person took a motor and they had this brilliant idea. Here was the motor shaft. Oh, and it wasn't long enough, so they put an extension on it to reach out here and to mount their gear on. Set of miter gears here. And they were doing this because they wanted to then transmit power down to another shaft. And this gear here was located in bearings. And I know what you're all thinking. Ooh, I'm scanning up and down my fundamental principles. Ooh, and that what he drew there, that really draws vacuum. That really violates, parentheses, it sucks, violates Saint-Venant's principle. Because here is the motor mounted here, and there's some bearings in the motor. And look at all this stuff here that's overhanging, that's unsupported. And you're probably also looking ahead to topic 6 with gears. And there are separation forces in the gear teeth. In other words, when this gear pushes on this gear, it pushes back, and there's actually, it wants to push away because of the shape of the gears, which is like a wedge. So it's going to push down, and as this gear here turns, if there's any torque put into this shaft, it's going to puck, 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 puck. It's going to kick it away and skip teeth. The structural loop being from this ground point to this ground point. This is the path of flow of the forces. Let me use a different color. See, the force flow, action and reaction, flows through here, through the bearings, through the ground loop, through the motor and its bearing set, through the shaft, back up into the gears. Applying your Saint-Venant's principle, you would then know that you need to, what? Get a set of bearings to support this guy as close as possible. So I can't push away, yet these bearings can't fight these bearings, so if this is dimension D, the distance here needs to be at least 5D, et cetera, et cetera. We're going to get to Saint-Venant's principle and bearings in a minute. But you see how it's not that, man, this dude is like really ADHD++. He's all over the map. No, this is what life is about, is being able to simultaneously think about a lot of very, very important stuff all at once without losing the focus of the problem you're at. It's like, think about it. You need to be focused and broad. The two form the circle of thought. You've got to do both at the same time. Got to think about everything and one thing all at once. Very critical skill. Professor Newton gives us that possibility. Conservation of energy. When we are designing a mechanism, think about this thing does something. That means I got to put something in order to get something out. Anytime anybody starts telling you, have I got a deal for you? You put in only 1 Newton meter of energy, and I'm going to give you 10 out. No. Let's do a little example here of how you would apply, for example, conservation of energy to a very, very simple problem. I have a bolt, and here's a nut. And for example, I'm going to use the bolt. I'm going to turn the bolt. As I turn the bolt, the nut moves. Ha. See? I'm not turning the bolt, but the nut is rotating and it's moving. I can also now not rotate the nut or let it move. And as I turn the bolt, it moves. I can turn the bolt, hold the nut, and the nut will move. All got that? Huh, that spins freely. If I hold this, how hard can I resist? In other words, when I apply a twisting or a torque, remember torque is I'm applying force at some distance like with a wrench. How much force does it cause in this nut as it wants to move back and forth? What does it do? Later on we'll talk about why it does that. We'll teach you the physics of how you can make this guy do this. Whee! How are we going to approach this? God, this is a problem hard. Very simple. Start with the fundamentals. Conservation of energy. Conservation means what? In times some efficiency, because this is the real world, equals out. Okay? In times efficiency equals out. What are we putting in? What are we putting in? And let's reverse this a little bit now because, well, here's the bolt head. So I have a wrench I'm going to put on my bolt head. And I'm going to put some force on it. And the force acts over some distance, L. And as I rotate this force, this wrench is going to go through some angle, theta. Force times length is a torque, which we draw by an arrow. And what is energy? Energy is a force applied over distance. Power, force applied, power times velocity. Okay? What is that? The in, force times the length, which is a torque, and we're going to apply it over some angle theta, it's the twist, and then we'll have some efficiency, that little cool dude, it's kind of a fancy little n, equals, and what do I get out? What do you want to get out? In this case, we want to know what is the force on the nut, because the nut is going to move back and forth. Remember, we're not going to allow the nut to turn. You've got another wrench on it. So we want to essentially know, what's the squishability of this guy? Well, that's going to equal the force on the nut. And you start saying, well, listen, I did some length over here and some angle. What's that here? Don't worry about that. The force on the nut times what? Conservation. There's a thread here that links the bolt to the nut. When you take any thread, and we're going to run this experiment here, put a little timing mark line on it, and I've got my tape measure. And we're going to set this up so I am at right at the number 6. Okay, so I'm going to rotate the nut through one rotation. And as I rotate through one rotation, it moved about, let's say 3/8 of an inch, a little less, about 8 millimeters. Okay? I would say it moved about 8 millimeters. This means that when I rotate the nut through 360 degrees, it moves 8 millimeters. Now you can't say theta is 360 degrees. You got to do everything in radians. And you should really you should eat up the idea of radians, because what it means is that gamma times 2 pi, you're going to eat it up. And 1 pi is not good enough. You've got to have all of it. You've got to have 2 pi's. Equals force on the nut times, this is called the lead. The lead is the linear distance traveled, right, in one full rotation. Conservation. I have put in a force that I'm applying through one full rotation, and what I'm getting out is a force on the nut being applied over one lead of the screw, one pitch. So by applying the conservation of energy, I can very easily solve for the force on the nut that I get out equals the torque I put in times 2 pi times the efficiency. This comes from the friction in the system, divided by the lead. Let's put some numbers in it. What can you do with this? Well, for example, you'll learn later how to calculate this efficiency, but for a typical just bolt and nut with sliding threads, the efficiency will end up being around 30% or 0.3. For something with rolling contact, such as this roller screw, the efficiency is much higher, 90 to 95%. We'll use 90% because the math is a little easier. The force I can get out equals 2 pi, which if you're on a diet, 2 pi is 6. And this is times 0.9 over the lead, which we said was 8 millimeters. And the torque I put in, let's say, oh, I'm just kind of a mellow dude, and the wrench is about this long, which is, let's say, what is that? A little over 1/3 of a meter. So 300 millimeters, let's call it 320 millimeters. And the force I'm going to put on, 20 newtons. Now, some of y'all thinking, newtons? What are you talking about, cookies? Well, a package of fig newtons weighs what? A good package of fig newtons I'm going to take home and eat for breakfast. Lots of good fruit in there. About a pound. And a pound is about 4.45 newtons or so. Call it 5 newtons because that's a really heavy cookie. Okay, so we'll do, that's when we said 20 newtons. Or that works out to what did we just say? About 4 packages of fig newtons, the big ones. 8 goes into 320, 40 times. What's 8 times 4? 32. So we have a multiplication factor of almost 40. Is that right? Yeah. 40 times 6 times 0.9 times 20. Look at this. 800 times 6 times 0.9. What's 6 times 0.9? You say, oh, that's 5.4 times 800. 5.4 for small values of 4 is equal to 5. What is 800 times 5? That you can do. 800 times 5 equals 4,000. You say, wait a second, what's he doing? He's a professor at MIT. Well, can't he just say, let's see, 800 times 5 is 400, or 4,000, and then 800 times 4 is 3,200, so the answer is 4,320. So what I just did here, you realize, is I applied Occam's razor to my initial design process. And I applied it in a conservative way. I'm trying to think, if I put this much force in, how much force can I get out? So what I've done is I want to move fast in my design world. I don't want to crash and burn like my little penguin friend just here did. You apply Occam's razor throughout your design process to be efficient, to get you rapidly enabled to see as a design feasible. Okay, so these very first order calculations, back of the envelope type calculations, you can do that sort of conservative estimation. 2 pi is 6 if you're on a diet. So you can use these little pneumonias so you don't get sick of doing the details. It all works out in the end because you're going to ultimately write a spreadsheet or MATLAB code and do the exact calculation. But this gets you there fast. Remember Occam's razor, you don't want to spend too much time in the early stages, because if it won't work with this number, if you're way off, boom, you're going to pick a different design. So I took 4 packages of cookies, 20 newtons, and turned them into 4,000 packages of cookies output. Now that is very, very good thing to do.